Hello, my friends. Welcome. Today, let's talk about variation functions. And this is kind of one of my favorite lessons. I've got a little story behind it. So get yourself some paper and pencil because we're going to be doing some thinking. And thinking means connecting things. So let's have a good record of it. All right, so let's go back and let's talk about something just really simple. Let's talk about a rectangle. So let me draw a little rectangle here. And let's say that the width of this rectangle is 6, but let's say that the length of the rectangle is something that I don't know. Let's call it L for the length. And so you recall that the area of a rectangle is equal to, well, it's the width times the length. So in this situation, the area then is equal to 6 times some unknown value of L. And let's just play around with some numbers a little bit. So let's say that the length is going to be, I don't know, 7 units long. So what's the area? Well, 6 times 7, the area would be 42 units, right? And let's decide, no, that's not enough. Let's make the length 8 units long. Well, what would that do to the area if I increased the length by 1 unit? Well, that would make the area go to 48. Notice that the area didn't go up by 1 unit, even though the length went up by 1 unit. The area went up quite a bit. Why is that? Well, because every unit of length is multiplied by the 6 for the width there. So what happens if I were to reduce it? Let's say that I had a length of, say, 5. So if I made the length go down, what would the area do? Well, the area would also go down, and it would go down to 30. So what we can really say here is there's a relationship between the area and the length. What we can say is that area varies directly as the length. And what this basically means is that if I increase the length, I increase the area. And if I decrease the length, I decrease the area. Sometimes this is said, instead of varies directly, it would be, say, directly proportional or something like that. In symbols, what we would say is this. We would say area, and then I would draw a symbol that looks like this. It's like a 3/4 of an infinity sign, and maybe it even should have some little curls there on the end, but I never kind of do the curls. But what to say, area is directly proportional to or varies directly as the length. I can't put an equal sign in there because the area doesn't equal the length. I can't say that the area is equal to the length. That would be a false statement, because if the length is 7, the area isn't 7. The area was 42. But if I were to go in here and put a number in that I multiply by the length by, let's say maybe squeeze in, oh, can I put a 6 in there? Yeah, there we go. Now I can use an equal symbol. Okay, so I can say that the area is equal to 6 times the length, whatever that is. That's a direct relationship, okay? A direct relationship is where you have one value equal to a constant, some number that does not change, multiplied by another value. That's just the simplest direct relationship. So if the second value, let's say the input value, let me just go ahead and make it an x and a y. So if I say y then would be equal to some constant, we're going to call that a k for constant, not c, but k. K times x. There's your basic direct relationship between k. We say y varies directly as x. If x gets bigger, y gets bigger. So if x goes up, y goes up. And if x goes down, y goes down. We see that with the area. You might see it in lots of other things, but that's your basic direct variation function. Y is equal to k times the x. It's multiplied. Now, this looks really similar to something that you probably have done before. If I said y is equal to mx plus b, well, it just means that my b value is 0, right? This is going to be y is equal to mx, where m is the same thing as the k. Now, when we had a y is equal to mx plus b, you remember on the graph that we would get a graph that looks something with the y-intercept being the b value. So it might come up here and cross right there on the y-axis. But with the direct variation equation, we don't have anything shifted up or down. It's got to come right through the origin. So the graph of a direct variation equation would look something like this, where that's your x and that's your y, and it has to come down here through the middle. So depending upon what your k value is, what your constant is, or what your slope is, if you want to think about it that way, then you would get the steepness of that line. So here's how we're going to play this out. You'll see lots of questions like this. This is great for like an SAT question or so forth like that. You'll see these that are just kind of generic variation equations and so forth. And I want to give you kind of a step-by-step process, kind of a sequence of how to sort this out. The key thing in here is you've got to translate how it communicates the relationship to you. So right here, it says if y varies directly as x. This I have to translate. I'm going to translate that by saying y, I'll do it up above. How do I translate varies directly? Varies directly is going to be equal to k multiplied by something, and then the next thing is going to be x. So I've kind of got three parts. I've got the y is the first part, that's the kind of like the output, and then varies directly as means equals k times something, and then the something that comes along is the x there. So the first step in answering this question is to translate it properly. There will be other statements that are different in their relationship, and you'll have to translate those properly. But for now, this is where we're going to start. So translate that. Y varies directly as x. So y is equal to k times x. Okay. And now it tells me y is equal to negative 16 when x is 6. These two go together. That phrase, that word there, when, that means that if x is 6, then y must be negative 16. Our first step here is to find out what the constant of variation is. So I'm going to use these two known values and plug them into this right here. What was the y value? Well, the y value was negative 16. And that's got to be equal to the constant, which is k, times the x value. Well, what was the x value when y was negative 16? Well, that would be 6. Okay. Now solve it for k. K is going to be equal to, oh no, it's a fraction, negative 8/3. All right. Okay. Okay. Now that I have the k value, I can come back up here to my general equation, and I can now make it specific to this situation. I can say for all y's, they're equal to the k value, negative 8/3 times x. This is now my specific equation that models this information. And now I come down to the final question. Hey, if this is true for this situation, and it must be true for all situations, then find x when y is equal to negative 4. Now that's easy. I got to find out what x is when y is negative 4. So y becomes negative 4, and that's equal to negative 8/3 times x. How do I solve when I'm multiplying by a fraction? Well, I just multiply by the reciprocal. So multiply the right-hand side by negative 3/8. Multiply this side by negative 3/8. Sorry, it's a little bit tight in there. Over on this side, these two are reciprocals and they cancel. So x is equal to, let's see here, this is 4 is going to cancel with that 8, leaving me a 2. Negative 3/2. There's my answer. Or as a decimal, if you wanted to do it that way, you could write it as a decimal. You could say x is equal to negative 1.5. Oh, wait a second. Is it negative? No, it's positive. It's positive 1.5. Negative divided by negative is negative, positive 1.5. Okay, there we go. So direct variation. Your sequence is to translate properly into a general, then use the known values, the two values that go together to find your constant, and then you use your constant in the specific equation to find whatever they ask you to find. There's a little different way to do it though, and this is the way that I like, and I don't see it oftentimes in textbooks. In fact, sometimes in textbooks they do it badly. Let me show you an alternate method. Remember I said that A varies directly as length, area varies directly as length. I said that could be maybe said as A is directly proportional to Maybe you've heard that before. Well, proportion means two fractions that are equal to each other. If I'm going to set these up as a proportion, a direct proportion would look like this. If I said y varies directly as x, let me back that up and say y is directly proportional to x. A proportion is two fractions that are set equal to each other. Here's how it would go. You would have the first x on top, the second x on bottom, and the first y value on top, and the second y value on the bottom. This is the best way to do it with the x's all in one column and the y's all in one column, and there's a reason for that that happens later. Oftentimes textbooks kind of mix all these up, and they'll give you equivalent proportions, but they won't do it structured where you have all of one thing on the left and all of another thing on the right, but that's useful later on. Notice here it's the sequencing that's important here. If this one goes 1 to 2, this one has to follow the same direction, 1 to 2. Okay, so now let me come up in here and let me do this problem using proportion, and you decide whether you like one or you like the other. So if y varies directly as x, all right, let me translate that right there. That says x1 compared to x2 is equal to y1 compared to y2. And now I have to go through here and identify first and second y's and x's. And here's my advice on how to do that. Come through here and I'm going to say and y, and that's the first one I come to. So I'll write y1 as a subscript. y1 is equal to negative 16 when x1 is equal to 6, because those two go together. Find x. Well, that's going to be the x2. Notice the subscript there of 2. When y2 is equal to negative 4. And now all I do is I just put the pieces in their proper spots. Okay, so then I'm going to do x1. What was x1? I don't know. I got to find it back up in there. Oh, x1 was 6, so 6 goes here. On the bottom, x2. What's x2? Well, I don't know. That's what I'm asked to find. So I'll just leave that as an x. You can call it x2 if you want to, but it'll be the only x floating around in there, so there's no need for a subscript. Then I go to the y's. y1 is on top on the right side fraction. Where's y1? Oh, there it is right there. So negative 16. And then y2, that was equal to negative 4. And now I just solved this proportion. And as you probably know, in order to solve a proportion, I find my variable, and then I multiply it by negative 16, negative 16x. I do cross multiply, but I really don't like that phrase. It really should be setting the cross products equal. So I'm going to take x times negative 16, and then I'm going to take 6 times negative 4 equals 6 times negative 4. And then all I have to do to solve this on the left is just divide by negative 16. So divide this by negative 16, and this cancels, and I get x is equal to whatever that fraction reduces to. And usually there's a reduction in there, so I'm not going to multiply the 6 times the 4. I'm going to go ahead and reduce it. So that becomes a 1, and that becomes a 4. And then the 6 and the 4 can be reduced. That's a 2 and that's a 3. Oh, look, there's my negative 3 halves. And I didn't have any fractions until the final end there. Okay. Neat. The goal with direct is to keep the direction going the same. x1 to x2 on top, and then y1 to y2 on the bottom. All right. Nifty. All right. Joint variation is when you've got more than one thing going on. So joint variation is when you have one value and it's equal to a constant times a second value times a third value or more, because you might have more than one thing going on. Like, for example, y'all know about triangles. Oh, let me see if I can draw a decent triangle here. Oh, that was a little warped, but it'll work. I've got my height in here, and then this whole thing right here is my base, right? You know that the base, the area of the triangle, had to salvage that, the area of the triangle is jointly proportional to the height times the base. Notice there's no equal sign in there, right? I'm just saying, I'm only focusing on the things that are important that I want to focus on. I'm just going to say, hey, area is proportional to the height and the base. There's other numbers in there, yeah, I know. but not variables, right? If I increase the base, I increase the area. If I increase the height, I also increase the area. And if I increase the height and the base at the same time, the area really gets big. Okay, so what's the constant that I have to put in there? Well, you remember that area is equal to 1/2 times the base times the height if you're going to do that, right? So my constant of variation here is going to be the 1/2. So, in fact, actually, in our discussion of the rectangle earlier, remember the rectangle earlier, and I made the width fixed. What if I didn't? I would say then that the area is equal to 1 times the width times the length. So my constant of variation there would be 1, and area would be jointly related to the width and the length. Okay, so how would you then do this with, say, an equation? It's going to be something like this. It's going to be something like y is equal to a constant times an x and maybe times something else, but it's all multiplied. You just got more than one thing going, like an x and z. And that's what we've got going on over here in this sample problem. So let's translate. Y varies jointly as x and z. Okay, so translate that. Y is equal to a constant, k, times an x times a z. You don't have to put the multiplication dots in there. I'm just doing it to be deliberate. And here's your information that you know. Y is 24 when x is -2 and z is equal to 1. Okay, so that's a known solution point or known solution set of values because there's more than 2 going on. Well, I have to have a known thing in order to then find the unknown thing. So I got to use the known things to find k. So I will use these values now to find my k. What was the y value? Well, it was 24 is equal to k. I don't know what that is yet. Multiplied by the x value. What was the x value? 2. And z was 1. All right, so now solve these for k. Hopefully quickly you can see that k is equal to 12. Isn't that nice? Now I can come up here and I can write my specific equation. Y is equal to 12 times the x times the z. And that's now my one that will give me anything else that I want. The next step then is, hey, find y when x is 12 and z is 2. New situation. Okay, so what's y? Well, that's equal to 12. That's the k. Well, look, x is also 12. Don't get them mixed up. You got 2 12s going on in there. And z is 2. So 12 times 12, that's 144, and that's gross. Times 2, y then is equal to, what, 288? There you go. Easy peasy. There's a way to do proportions with joint, but it's a little complicated and I kind of don't want to go into it right at this moment, so we're going to pass on that. All right, so up until now we've been doing things that are multiplied together. Guess what? You do things that are inverse. Okay, inverse now is this. Inverse says you've got one value and it's equal to a constant. And if it's not multiplied, guess what it is? And divided by another value. So if I were doing just general x's and y's, I would say if y is inversely proportional to x or varies inversely. Yeah, let me do that. I'm mixing two different terminologies here and I don't want to do that. If I said y varies inversely as x, it would look like this. Y is equal to a constant. Never forget the constant. There's always a constant in there, even if it's 1. K divided by x. That would be my general relationship. What this means is this. Previously, when the input went up, the output went up. And then when the input went down, the output went down. That was direct. Inverse says it goes the opposite direction. So if I increase one thing, the other thing has to decrease. Okay, as the denominator, as you can see in the fraction here, if I make x bigger by itself, the denominator gets bigger, which makes the entire fraction get smaller. Let me see if I can give you a simple example for that. Let's say that, here, let me just multiply both sides by x, and I would get this. I would get x times y is equal to 12, or equal to k, and I want it to be equal to 12. So if I said x times y is equal to 12, 12 is my constant here, and let's say x was 4. What does y have to be in order to make 12 when you multiply them? Well, that would be 3. Okay, I still want my constant to be 12. But let's now say that I want to decrease my x value, make the x value smaller. Let's make the x value 1. What does the y have to be equal to now in order to give me 12 as a product? It's got to increase. It's got to go up to 12. You see what I'm saying? So the x changed by getting smaller, 4 to 1. But if the one value got smaller, the other value had to get bigger. Okay, so let's see how that would play itself out with an example question. And this one's worded a little bit differently. You got to be sharp now. You've got to read to understand. If a varies inversely, what? If a varies? What are you talking about? No, A is A. If A as a symbol, not as a word A. If A as a replacement for a number. If A varies inversely as B, okay, translate that. A is equal to a constant divided by B. There's my general relationship. And A equals 4. That would be like this. A equals 4. When B equals 12, so B is equal to 12. That's the group that goes together. Find B then when A is equal to 7. So this is the known here, and I got to use it to find the unknown. But the first thing I have to do is I have to find my constant. So I replace my A and B with what I know that they are. A was 4, and that equals a constant divided by B, which is 12. And we solve for K by multiplying both sides by 12. I get K is equal to 48. So now I take this and I plug it back up in there, and I get a specific relationship now. A is equal to 48 divided by B. That's my specific equation. Now let's find the new thing. I'll even switch colors. Find B when A equals 7. So put 7 in there. 7 is equal to 48 divided by B. And as you probably know, when you solve an equation with the variable in the denominator like this, the B comes up and the 7 goes down. And so B then is equal to 48 divided by 7. And I don't think that reduces. So there I go. I'm done. There's a way that you can do it with proportions now. So let's talk about how to do it with proportions. With proportions, A varies inversely as, or Y varies inversely as X is what I said here. How would you do that proportion? It would say Y is inversely proportional to X. It looks like this. Again, you're going to have two fractions that are equal to each other, but watch carefully. Let's see here. I'm going to do x1 compared to x2. But now it's going to be y to y, 2 to 1. It goes the opposite direction. And that kind of makes sense because remember when we did the changing out with the things that multiplied to give me 12? If I made one bigger, I had to make the other one smaller. So you've got to really be sharp here. And inverse says if this goes 1 to 2 on the left, this goes 1 to 2 the other direction on the right. Okay, so now let's come over here and let's try this one. And we'll see what we can do with a proportion. So A varies inversely as B. Okay, so that would be an A1 compared to an A2 is equal to a B2 compared to a B1. Great. Now let me plug in the values. Oh, let me go through and identify 1s and 2s. Okay, and A equals 4, that would be A1, because that's the first thing I come to. A1 equals 4 when B1, because they go together, equals 12. Find B2, not your vitamin, but B2, when A2 equals 7. And now I have to be very careful how I plug the numbers in. My instinct, and yours too, is to, if it goes 1 to 2 on the left, is to make it 1 to 2 on the right. You've got to really pay attention and not goof it up. What is A1? A1 is 4, so I'll put a 4 there. What is A2? A2 equals 7, so I put a 7 there. Now, not B1, it's B2. B2 on top. Find B2. Well, I don't know what that is, so that's my unknown B. When B1 equals 12, so there's 12. Okay, now set the cross products equal. 7B is equal to 4 times 12, and then divide by 7, and simplify. B is equal to, well, there we go, 48 sevenths. Nice. Okay, so if you're going to do it with proportions, make sure that you switch the direction. Okay, that's inverse. Now, the last one that we're really going to do technically is called combined variation, and that's when you got some on top and some on bottom and things like that. So really, it's kind of something like you got multiple things going here. It's a combination of things. Well, I guess that's why they call it combined. Let's just jump right in. Okay. Oh no, here I want to say this. If it says direct, it goes in the numerator. And if it says inverse or inversely, it goes in the denominator. But don't forget your K. All right, so now here we go. Suppose P varies directly as R and inversely as T. I've got to translate that. P varies directly, which means it's equal to a K. Don't forget your constant. Directly means times. Times what? R. But then it says here inversely as T. So it's divided by now T. All in one package. Okay, there we go. Now, careful reading here. Find T when R is 10 and P is -5. I'll do that in blue. That's the blue family. If T is 20 when P is 4 and R is 2, I'll call this the purple family. The purple family is the known. That's a group where you know all the pieces that fit into the puzzle. The blue is the unknown. So I need to use the known values first. So I'm going to take these values and plug them in because I have to find my constant. I have to find K. So what is P? Well, it tells me P is 4. So 4 then is equal to a constant K multiplied by an R value. What was the R value in that family? 2 divided by T. What was the T value? 20. And if I multiply by 20 and divide by 2, I get a K value of 40. Okay. So now I come back over here and I can use it to find the new unknown. So P is equal to 40 R over T. That's my specific equation. Now I use the blue values. Find T when R is 10 and P is -5. So P is -5. That equals 40 times the R value, which is what I don't know. So I guess I don't need parentheses. 40R divided by, no, my mistake. I do know R. R is 10. I see, not having the equal sign mess with me. I wrote that to mess with you. And it messed with me. Well, I think I'm getting it, okay? So, and then we're supposed to find T. T is what we're supposed to find. All right, so again, the T comes up, the -5 replaces it, goes down. So T is equal to 40 times 10 divided by -5. And cancels, there is a 2. And I get, what did I get, -80? Okay. That's about it for the assignment thing, but I want to share something extra with you. Okay, let's talk for just a moment about powers. Do you remember the formula for the area of a circle if I know a radius r? Remember that? Remember that area is equal to pi r squared? So can't I say that area then is equal to some constant of variation, which is pi, times r squared? Yeah? So I can say then area is proportional to r squared. Area goes by the square of the radius of a circle. So let's play with something here. If I said the area is equal to pi r squared, and I just let r is equal to 1 squared. Okay, what's that area? That area is pi. Let me now double the area. So it's equal to pi times, I'm sorry, double the radius. Double the radius, 2 squared. What's 2 squared? That's 4. So what's my final answer? 4 pi. And I want you to notice something here. I doubled the radius. What did I do to the area? How does this area change into that area? This is multiplied by 2 squared. It's multiplied by 4. If you double the radius, you don't double the area. You quadruple it. What if I were to triple the area? I'm sorry, triple the radius. I keep getting ahead of myself. Triple the radius. So 3 squared. What's that? Well, that's 9 pi. Okay, let's go back and talk about what changed from the first part. Okay, instead of doubling the radius, I tripled the radius. Radius times 3. What happened to the area between here and there? Multiplied by 9. So what's really going on is this. Whatever I do to the radius, I have to square that to tell me what happens to the area. That's nifty. Now, proportionally, this is where it's important to keep the things in their separate columns. Proportionately, I would say that the radius 1 is directly related to the area 1, right? As the radius got bigger, the area got bigger. But here's how it went bigger. It got bigger only if I squared the radius. So you see, I needed the r's all in one column on the left and the a's all in one column on the right. And the early scientists, the natural philosophers like Galileo and Newton and Kepler and so forth, they didn't use equations. I still remember going back and reading, somebody put the works of Galileo, not a book about Galileo, but Galileo, right? Put a book of Galileo in my hand and said, hey, you physics guy, you need to read this. I thought, I was in physics a long time in college, and nobody ever asked me to read a book about Galileo. Nobody even asked me to read Galileo, but gee, I think if you're going to study physics, you should study the writings of Galileo. So I thought, I like pendulums. I'll go find Galileo's work on pendulums. Pendulums look like this. Every high school physics student knows that the period of a pendulum is 2 times pi times the square root of the length of the pendulum divided by the acceleration of gravity, g. So I thought that'll be easy for me to find. I'll flip through the book here. I'll find out where he talks about pendulums because I want to read about how Galileo talked about pendulums. I couldn't find the equation. What I did find was this. He says the times of vibration bear to each other as the square roots of the lengths. Galileo is thinking proportionately. He is not thinking in terms of an equation. Where's the pi? Where's the 2? Where's the g? Doesn't have to be there. Because if you do it proportionally, all the clutter cancels out and you can focus just on the relationships. That's what he did. This is how the early scientists actually figured out the relationships. The equations came later. This, as a mathematical art, this is music. Okay? Music is relative quantity. The important thing is how the things relate to each other. What is their proportion? Is it direct? Is it inverse? Does it go by the square? Does it go by the cube? Kepler had one that went by the square on one side and went by the cube on the other side. And that was how these things are discovered. The equations come out later. Anyway, let's pursue happiness. And then with the wisdom and virtue as our guides, obtain it.